This is the 10th lecture of the course MTH 204A for section B. Recall that in the last lecture we have discussed Schurz Lemma. So, this is the statement of Schurz Lemma that if we are given two representations of if we are given two representations of a group G, then if the representations are not isomorphic, then the space of all G invariant maps from V to W, which is also written as home G V W, because in general home is the much more general algebraic term. So, so this vector space is trivial if these are not isomorphic. On the other hand, if the spaces are equal, provided the field is algebraically closed, for example C, and the dimension is finite, then home VV, the vector space of all G invariant linear maps from V to itself, which is also written as the G invariant the space of all G invariant endomorphisms of V is isomorphic to C as a vector space. So, this isomorphism is as vector spaces over the field of complex numbers. This is because if you remember that all G invariant endomorphisms of V are precisely the scalar multiples of identity. So, this lecture will start with some corollaries of this. In the last lecture we have discussed a few corollaries. So, in this lecture we will discuss some more. In the beginning, then we will go for general actions. So, now assume that, so this is a corollary. Assume that the group G is abelian. G is abelian. Therefore, we see that the abelian, and let V rho be a representation finite dimensional representation, irreducible representation of course, irreducible representation of this abelian group G. So, then it is quite clear that for each x in G we do have this map, this commutative diagram. So, this is rho x. So, this is rho x, rho G, again rho x, rho G. So, this diagram commutes because x and G for every x and for every G. Okay. So, this diagram commutes. Therefore, we see that this rho G belongs to this end G V, and because the rho G is of course a linear map, and then we see that it commutes with it becomes G invariant since the group is abelian, and hence it follows that rho G must be of this forms lambda G times identity for some lambda G in for some complex number lambda G. So, what does that show? That shows us the following, that if we start with any vector V, let us say for every non-zero vector V, irreducible, yeah. So, for every non-zero vector V, okay. So, here of course throughout we have assumed that the spaces on which we are considering the representation, the spaces are non-trivial, because otherwise there is no point of considering invertible linear maps. So, for every vector non-zero we see that rho G V being lambda G V lies in the linear span of V. Hence, it is quite clear that from this that C V, this subspace of V is G invariant. Okay. Now, from the irreducibility it follows that V must be equal to this C V, that is dimension of V is 1. Now, so what we have proved is if a group is abelian, no matter whether finite or not, then every finite dimensional irreducible. So, yeah, so every finite dimensional irreducible representation of G must be of dimension 1. So, if G is abelian, it does not admit any two-dimensional irreducible, two or higher dimensional irreducible representations. Okay. So, this is what we obtain. In fact, later on we will see that this condition is also sufficient, that is if for a, of course for finite groups, if for a finite group all the irreducible representations are, so here of course the field is over C. So, every finite dimensional, so yeah, so if we can, later on we will see that for a finite group, if it happens that it's every finite dimension, it's all finite dimensional irreducible complex representations are of dimension 1, then the group will be abelian. We will prove that later. So, right now we have just proved the converse, but it's somewhat general that we do not care whether the group is finite or not. So, as long as the group is abelian, then it's any finite dimensional irreducible representation will necessarily have dimension 1. Okay. Next, let us come to the second corollary. So, as an immediate consequence of this, so let G be a subgroup of G, L and C, an abelian subgroup. Again, I do not care whether the group, this is finite or not, this is some abelian subgroup. Then what do we see? Then we see the abelian subgroup, and let V rho be a representation of G. V rho be a representation of G. Okay. Well, at least for this we need to what we are going to do now, for that we need to assume G is finite. So, recall that we have proved that for any finite group for any and of course finite dimensional representation dimension of V is finite. So, there exists subspaces W1 up to Wk, invariant subspaces, G invariant subspaces, G invariant subspaces, such that V is. So, this is what we proved. This is what is called the Muskies theorem, which we proved earlier, and each subrepresentation is irreducible. Subrepresentation is irreducible. Now, since G is abelian, what we obtain from this is each Wi must be of dimension 1. So, therefore, we see that so this is of this form CVK, and from this it follows that V1, V2, Vk is a common eigenbasis, because since this is a one dimensional subspace, since this is G invariant, so that means V1 has to be an eigenvalue for all rho G's. So, it is a common eigenbasis, eigenbasis for this family of linear invertible linear maps. Okay. That means we do have a single eigenbasis for all the linear operators rho G. So, thus I mean it follows that there exists a invertible matrix, so such that for every G in G, P inverse rho G P is diagonal. So, in this situation, if we are given an abelian subgroup of G, L and C, then we do have a common eigenbasis for we do. So, if we are given a finite abelian subgroup of G, L and C, then we can diagonalize all the matrices of G simultaneously, that is by a single ordered basis or by a single invertible matrix we can make all of them diagonal. Here I should make some more comments that which maybe I should have said earlier. So what is that? It is very simple that suppose V rho is suppose G has a representation, V rho is a representation of G, and we do have decompositions like this. So all the W1 up to Wk are G invariant subspaces. Suppose this is given. So and assume V has dimension finite. So if for each I, if I choose a basis, an ordered basis of Wi for all I, then B1 union Bk is going to be a basis for V, and then we see that for every G in G, what is the matrix of this operator rho G with respect to this, we see that that is nothing but it will be of this form. If we just write it mg, so this is basically somewhat m1g to mkg. So mig is nothing but the matrix of the restriction of rho g on wi with respect to the ordered basis bi. So in general, so this is what we see in generality, that we can choose a single basis with respect to which we can bring all the matrices in the block diagonal form. This holds for any representation as long as there is as long as we have a decomposition. So as long as we have a decomposition by a single choice of ordered basis, we can make all the matrices block diagonal. In addition to that, if things are abelian, then we see that of course finite abelian group and of matrices, then we can make all the matrices diagonal by choosing a single eigenbasis. Okay, fine. And then another consequence of this is the following. Well, maybe not a consequence of this. Yeah, not a consequence of this. We need to do something else. All right. So let V is an inner product space over C. Right now I do not care whether it is finite dimensional or not. Inner product space over C by U of V. This is the group of all unitary operators on V, that is invertible linear maps that preserves the inner product. So if we have a representation, for a group G of G such that for each small g in capital G, rho G lies in UV, that is all the operators that group elements are producing are unitary operators, invertible unitary operators, then we say that the representation is unitary. Okay, the representation is unitary. In particular, so if V is finite dimensional, then every representation of of any finite group G can be made unitary will explain what this means, what this means. So, since V is a finite dimensional vector space over C, it is isomorphic to some Cn. So, you can choose an inner product, you can choose an inner product on V. So, is a finite dimensional, you can choose an inner. So, okay, just a minute. So, so here we just assume B is a finite dimensional vector space over C. Inner product I do not need to choose in the beginning. So, since V is a finite dimensional over C, so we can choose an inner product on V, and then from that we can define another inner product on the same V, which is defined by this, that X and Y. This new, let us denote this new inner product by G. Simply we have done this earlier, that simply we take rho G X and rho G Y. Okay. So, this is the chosen inner product, and then from that we are defining a new inner product. So, with respect to this new inner product, we can easily see that for every J, let us say if you want to write G prime, in G, rho G X, rho G prime X, rho G prime Y is nothing but inner product of X, Y. So, thus with respect to this inner product, of course, I should write this, with respect to this inner product, we see that all the operators are unitary. Okay, all the operators are unitary. All the operators are unitary. So, let us say so let me again remind you that here we have changed the inner product. Okay. Now, what do you obtain as a consequence of this? So, okay. So, thus each rho G prime is unitary. Okay. Now, rho G prime is unitary. So, therefore, okay. So, what we can do now is the following, that from this it follows that as a consequence that if G is a finite subgroup of, if G is a finite subgroup of this of GLNC, then it is conjugate to some subgroup of the UNC. So, there exists an invertible matrix, such that P inverse GP contain inside the group of all unitary matrices. This is because we can change the inner product on Cn. So, G has a natural representation on Cn, right. So, we can then change the inner product in Cn. So, thus we can make all the matrices unitary, okay. And from that, this is just an immediate consequence. I leave the details to you. Okay. So, what I was since in this new inner product space each rho G prime is unitary. So, if you choose an orthonormal basis of this new inner product space, then all these matrices will be unitary, right. So, thus from this it immediately follows that by a single invertible matrix we can, if we by a single invertible matrix, if we conjugate by a suitable single invertible matrix, we conjugate this group, we will land inside the unitary group. So, that is what we have proved. Every finite subgroup of GLNC is conjugate to some subgroup of the unitary group. Okay. So, enough of representations. Now, again let us come back to general group actions. Since recall that in the last lecture we have proved that for any action of G on a set X and for any X we have seen that this G space and this G space, these two G spaces are isomorphic. We do, and in the setup when G is finite, we in fact obtain that so this is called the we in fact obtain that so this is called the orbit stabilizer theorem. In fact, this is actually you see this is a counting formula which turns out to be very useful. One application I have already told you, one or two applications. Also using this we proved that if G is a finite P group where P is a prime, then ZG is non-trivial. So how did we prove that? So for this action, so we consider the action of P on this set itself. Therefore, we have seen that G is nothing but ZG plus the, so we consider the action of G on itself by conjugation. So if move that and then the non-trivial orbits. Let's if we denote those non-trivial orbits by C1 up to Ck, then each of these non-trivial orbits are the orders are for each of these terms. Each of these terms is divisible by P, and then P has to divide this. But since identity lies in ZG, this has to be greater or equal to 1. So if P divides this and the quantity is greater or equal to 1, so from that it follows that this is at least P. In fact, here we can say also something more. So let me do that. I missed that in the last lecture. So in addition to that, let H be a non-trivial normal subgroup of G, okay, non-trivial normal subgroup. So since this is normal, we can consider the action of G on H by conjugation. Because of this normality, H is invariant under the action, and therefore again we can write the same thing. So H will be H. So in the action of G on H by conjugation, we see that first of all this is the first term will be the fixed point of that action, and fixed point means so GH, G inverse will be H for every G, that means H has to be in the center. So thus the fixed point of this action is nothing but then there are other non-trivial orbits, but what we know about them is all those terms are divisible by P. Hence as expected it follows that so it is clear that this is divisible by P. This is divisible by P, and this is of course at least 1 because identity is there. Hence this has also order P. So thus we in fact prove something stronger, that every non-trivial normal subgroup of G, every non-trivial normal subgroup of G intersects the center of G non-trivially. And in particular, if G itself has order P, then G has to be contained in the center. That is, we prove that every normal subgroup of G of order P has to be contained inside the center. So this is what we obtain as a consequence of that counting formula. Now let me give you another application of this counting formula. So what I am going to show you now, I am sure that you must have seen this earlier, but however I am showing this to you just to show you the power of this formula, that it indeed produces many of the results that you are already familiar with. So let G be a group and H and K. So, assume that G is finite, H and K are two subgroups of G. So, HK is the collection of all elements of this form, H equal to H and K belonging to K. We can consider the following action of H cross K on HK. In the action is defined in this way. H and K, it maps to, so take a typical element here, let us say xy, so it maps x K inverse. So for all H x belonging to H and y K belonging to K. So on a typical element, okay, I should rather put it in this way, that H K and then x y. So maybe the better way of doing that is I should simply skip saying x y. So take any x, H x K inverse, yeah. So for all x in H K, H in H and K in K. Okay. It is easy to see that this defines an action of H cross K on this set, and again we can immediately see that this action is irreducible because we can move. So the identity lies in this HK, we can move that to any element, typical element HK of HK if we apply if we apply this element from the pair on this one, then we will get HK. So this action is irreducible. Hence, now we are used to, since it is irreducible, we can immediately use the this counting formula. So this by stabilizer of 1 is same as the order of, yeah, so order of HK. Now what is the stabilizer of 1? So if H comma K stabilizes 1, that means we must have H K inverse equal to identity, right? H K identity, that means H has to be equal to K. So H is in H, K is in K, so therefore that means both of them have to be in the intersection. So thus we see that the stabilizer of 1 is the intersection, therefore we have seen this for this well known formula which you might have proved otherwise, but here it also follows as a consequence of this counting formula which is known as the orbit stabilizer theorem. Anyway, so let us go ahead. So let me now talk about concrete examples of orbits and stabilizers. We have already defined them and discussed why they are important. Now this is the time to find orbits and stabilizers for concrete in the context of several concrete examples. So let me, so this in this lecture, yeah. So in this lecture I will be mostly confined with the cases, with the situations when either the permutation, yeah, I will be mostly confined with the actions of the permutation groups or the actions of linear groups. In the next lecture we will see other kinds of examples. So the first example is, I should rule out that case in the very beginning. There is the trivial action. So if G is any group and it acts on any set trivially, then it is easy to see that the orbit of any point is singleton and the stabilizer is the whole group. So like we are done with the formality. Now let us start start discussions about more interesting actions. So if X is a non-empty set, then consider the action of Sx on X. So this action is irreducible. Well, so this is the time when I should shift to the standard terminology. So the standard terminology is the actions which we call irreducible. In literature they are called transitive. So they are the exactly same thing. Okay, so what this means is for x, z, x and y, we have a group element G such that Gx equal to y. Okay. All right. So this action is of course transitive. In particular, for any n, the action of Sn on 1 up to n is transitive. And in the last lecture we have left this exercise that two orbits, if we take 2 points from the same orbit, then the stabilizers are going to be conjugate to each other, therefore they will have the same number of elements. So therefore in case of in case of this action, whichever point we pick up, the stabilizers will be up to conjugation the same. So what is the stabilizer of n? That means all permutations that fixes n. So all permutations of 1 up to n that fixes n, that collects, that subgroup is naturally isomorphic to Sn minus 1. Therefore we see that so here orbit of n, orbit of anything is the whole set 1 up to n, and the stabilizer of n is nothing but is isomorphic to Sn minus, and naturally we have a bijection between this and this. Okay. So this is quite simple. Now if we take an, what will happen? The action of an on 1 up to n is also transitive, and just like the same. So the stabilizer of n is the collection of all even permutations that fixes n. So naturally this is, the stabilizer is isomorphic to an minus 1. Okay. So you see that it is basically a permutation, it can be regarded naturally a permutation of n minus 1 symbols, and that permutation is even. Therefore the stabilizer is isomorphic to n minus 1. So here also we have thus there is a bijection between this and 1 up to n. Okay. Now what about another important subgroup of Sn, namely dihedral group? For dihedral group thing, the situation is slightly non-trivial. So what about dihedral group? The action of dihedral group on 1 up to n is already we have seen that to be transitive. So in this case, what is the stabilizer of any point here? So the orbit stabilizer theorem says that, so dihedral group has order 2n, the orbit of any point has order n, so therefore stabilizer of every point should be of order 2. So of course one of the stabilizing group elements will be the identity, so there should be another thing, and that will has order 2, so that means that other element in the stabilizer has to be a reflection. So which reflection? So I will let me leave it to you to find that algebraically, but geometrically it is quite evident that suppose if this is my regular polygon, 1, 2, 3, 4, 5, n minus 1, n minus 2. So what is the symmetry that is fixing a given point? That is exactly the deflection with respect to the deflection. If we join this vertex with the center of the circumcircle, well, the circle is quite is looking horribly, but however, so if we consider the reflection with respect to this line, then this is that reflection, this is that symmetry which is going to leave that point fixed. So, this is the geometric description. The algebraic description I am leaving to you to work out. Another example of an action of D to n is its action on this set of all edges. So, the D to n, the action of all sides of Tn, this is also transitive, because by rotating you can send any side to another side. So, here also the stabilizer of every side will have exactly 2 elements, stabilizer has order 2. Okay. So, given a side, what is the symmetry of the polygon that is leaving that side fixed? What is the symmetry? So, let us first take a few special cases, then we will understand. So, n equal to 3, you see this bisector of this side is indeed an angle bisector as well. So, with respect to this angle bisector or the side bisector, if we take the reflection, then this is going to leave the side fixed. Similarly, for n equal to 4, the situation is that like when n is odd, you can see that all the angle bisectors are, they coincide with the side bisectors, because every angle bisector will be a bisector of the side opposite to that. But when n is even, then this is certainly not the case, because if n is even, then every angle, if you take an angle bisector, this will be automatically a common angle bisector of the angle which is diametrically opposite, whose vertex is diametrically opposite to that. Therefore, when n is even, what are the, then this d to n is nothing but all the, in d to n we have, apart from the rotations, all the angle bisectors and the side bisectors as well. Try to understand geometrically what are the elements in d to n. So, we have rotations, then when n is odd, then considering all the angle bisectors will be enough, right. But when n is even, that is not enough, we need to consider the side bisectors as well. So, thus for D8, this apart from the rotations, this is one. So, this is one axis of symmetry, this is one axis of symmetry, then we do have the angle bisectors as well. So, these are the 4 axes of reflections. Okay. So, thus you see that like the stabilizer of any given side is basically the reflection with respect to the bisector of that side. As I said, when n is odd, then that bisector coincides with some angle bisector, but that is not the case when n is even. Okay. So, the action of d to n on the set of all sides is clear, that is transitive, and for any given vertex of side, these are the stabilizers. Okay. Let me see whether I have finished whatever I was supposed to talk. I forgot one thing. Okay. So, let us do that. So, let us come back to this example. So, this is the main example, that whenever Sn is acting, then any subgroup of Sn will act. Now, let us consider the action of the following subgroup of Sn. So, let sigma lie in Sn, we consider the cyclic subgroup generated by sigma that also acts on this set 1 up to n. Okay. So, for this action need not be transitive, right. For example, if you start with a transposition, certainly and n is, let us say, greater or equal to 3, then certainly that is not going to be transitive. So, then the question is, what is the odd bits of this under this action? Do we have some description of those odd bits in terms of the given sigma? Yes, we do have. So, so we know that we have it is well known that sigma can be written as a product of disjoint cycles. So, these are the products of disjoint cycles, disjoint cycles, Well, it is customary to omit the cycles having length 1, cycles of length at least. Okay, so what I was talking about is in the action of the subgroup generated by sigma on this set, we would like to know the orbits under this action, and the question was whether we can describe the orbits in terms of the sigma. So, let sigma 1 up to sigma k be disjoint cycles such that whose product is sigma. We know that such sigma is exist, and it is customary to remove the cycles with length 1. So, these are the disjoint cycles of having length at least 2. So, any sigma I, it looks like this, that some ai, then it will be sigma ai. So, then it will go up to some sigma li minus 1 ai. So, let li be the length of sigma I. Let Li be Li, which is greater or equal to 2. So, let each sigma I be this cycle. Okay. Then it is easy to see that sigma I, sigma to the power Li minus 1 ai, I from 1 up to k. So, I from 1 up to k. So, is the collection. So, for each I we have a subset. So, this k subsets together with the fixed points, gives us all the orbits under this action. That is quite clear from here, because this is one orbit, that is clear. So, for each sigma I, this set is easily seen to be an orbit. So, these are thus we get all the non-trivial orbits, and the trivial orbits are coming from the fixed points. So, if sigma is equal to sigma 1 up to sigma k, where these are the disjoint cycles having length at least 2, then from that we can immediately see that then from these cycles we obtain. So, from each of these cycles we obtain one orbit, and together with the fixed point we describe all the orbits in terms of sigma. Okay. So, thus we see that from any cycle decomposition of sigma we obtain the orbits, and this also gives us something interesting. So, try to again analyze this proof. This proof shows that whenever sigma can be written as a product of disjoint cycles, then from that product, for each of the terms in that product, we get one from each of the terms in the product, they correspond to some non-trivial orbit, and together with the fixed points we get all the orbits. So, what does that tell us? Then tells us that this decomposition of sigma into the product of disjoint cycles must be unique. I repeat, this is because if sigma is the product of some other, let us say tau 1 up to tau r, where each tau I is a cycle of length at least 2, then for those tau i's we should get, so from those tau i's we should get all the, so those tau i's should correspond all the non-trivial orbits, and then we do have the fixed points which are giving us the typical trivial orbits. Therefore, we see that each tau I must correspond some sigma j, okay, because from the orbits that we obtain from the tau i's and the orbits that we obtain from the sigma j's must be the same non-trivial orbits of under the action, because given an action its orbits are unique. So, therefore, if two decompositions are there, then from the decompositions, from the first one the non-trivial orbits that we obtain and the second one the non-trivial orbits that we obtain, they must be same. Thus, this shows that given any sigma this decomposition is unique. up to the rearrangement of the factors. So, let me just put a remark here. This in fact proves the uniqueness of cycle decomposition. Of course, one can prove the uniqueness in different ways, uniqueness of cycle, but this is one way, that is so just by observing that each of these cycles actually corresponding to some non-trivial orbit, and then from the uniqueness of orbits we obtain the uniqueness of this decomposition, uniqueness of cycle decompositions. Of course, what a uniqueness is up to a rearrangement, up to a rearrangement of the factors. Okay. Okay, so when we consider this special subgroup generated by when we consider any cyclic subgroup of Sn, then the orbits are exactly given by the factors appearing in the cyclic decomposition of the generator of that subgroup. And it is also now quite easy to see what the stabilizers of points are. So, for the trivial orbits, of course, the stabilizer is the whole subgroup, and this whole subgroup just a minute. And for any point whose orbit is non-trivial. So, if A is a point which is moved by sigma, then A must be moved by one of these sigma i's. So, without loss in generality, we may assume that A is in sigma I, A is in sigma 1, then it is quite clear that from the disjointness sigma 2 up to sigma k, all fixes A, okay, all fixes A, and yeah, so sigma 2 to sigma, all this fixes A, and any power of sigma I. So, if sigma 1 has length L1, then since sigma 1 is a cycle, any power of sigma 1 which is not a multiple of L1 is not going to fix A. Okay. So, therefore, it is quite clear that the stabilizer of this point A is the subgroup generated by sigma 1 up to sigma k, because all of them are fixing. So, try to again understand that any element in this group will be of this form, sigma to the power, let us say some m, since they are disjoint, will be some sigma 1 to the power m up to sigma k to the power m, and sigma 1 to the power m is not going to. So, sigma to the power m is going to be sigma 1 to the power m to sigma k to the power m, and if m is not a multiple of L1, then we see that I think I said something wrong, let us see. So, if m is not divisible by L1, then certainly sigma m a will be moved by, so sigma a will not equal to a, because other factors are not creating any disturbance, but this one is indeed moving. Therefore, yeah, sorry, this yeah, so I was wrong, yeah, that is fine, now it will be fine. So, sigma, yeah, and just a minute, yeah, and once m is divisible by L1, then certainly I mean anyway these points are fixing this, and therefore yeah, so therefore we do have that sigma L1 n, well I should not use n again, see n of A is A for all n in Z. Okay. So hence the stabilizer of A is this precisely this group, this group generated by sigma L1, because only sigma L1 brings A back to its position. Okay. So thus we have thus we have seen the orbits and stabilizers of the actions under the actions of some important subgroups of Sn. Now let us move to linear action of linear groups. So okay, we will roughly talk about the actions of the linear, general, special and orthogonal groups. So let us do this step by step. Okay, so let us start with the vector space V. So V is a vector space over F. Okay, so we consider GLV. GLV acts on V. So what are the orbits under this action? So this is the standard action. First of all, 0, the orbit of the origin is orbit of this null vector is the singleton null vector, right? And then any non-zero vector can be moved to any other non-zero vector by some invertible linear map. Therefore, the orbits under these actions are precisely this. So this is for any vector space V. If furthermore we assume that the dimension of the vector space is infinity and at least 2, then we can then we should be able to consider the special linear group of V that also acts on V in the natural way. And what are the orbits under this action? That's also quite clear that yeah, that's also quite clear that these are the only 2 orbits. This is because of the following, that it's in order to show, so in order to show this is the orbit, it's enough to show that every non-zero vector. So if we start with let's first fix a basis of E1 up to E, ordered basis of V. It's enough to show that for every non-zero vector V, E1 can be moved to V by some linear map having determinant 1. So now it is quite clear that how to deal with that, because yes, so what we should do is, so we know that there is a linear map, such that T E1 equal to V, okay. There is a linear map, and if V is nothing but let us say alpha 1 E1, alpha n En, then the matrix of T with respect to this ordered basis is nothing, has the first column will be alpha 1 up to alpha n. Okay. There might be something else which I do not care, but however the important part is this is an invertible matrix. Okay. Now we have to so I do not know what the determinant of this matrix is. So let D be the determinant of this matrix. Determinant, let this be D. The idea for making it idea for choosing an appropriate T from SLV is that we would like to divide one column of this matrix by this D. This is what we want to do. So yeah, so what we can do is that yes, So, consider this new matrix, let us say the second column. So, consider this invertible matrix where the second column we have divided, so C2 by D, and then let the other columns be as usual. Okay. So, this is call this matrix to be the matrix A. So, certainly A has determinant 1, certainly A has determinant 1, and this matrix A automatically gives rise to a linear operator, on the vector space V. So, consider the linear operator S, consider the linear operator S, linear operator, because we have fixed a basis, linear operator S. So, let us denote this basis by script B. Consider the linear operator S such that this A, okay. And then it is quite easy to see that S of E1 is certainly going to be V, because that is how that is the exact we are exploiting the connections between linear operators and its corresponding matrices. So, we see that I mean how to compute this. So, we can write down the coordinates of this basis vector and then get the basis that column vector multiplied by the matrix of S, and then whatever we get from that we can capture the given image. Now, what we can see is we are getting alpha naught to alpha n. So, therefore, putting them with the base, taking the combination with them, we get V. So, thus the action of SLV is also transitive, and as usual here well in the to see things more concretely, let us take V equal to Fn, then we can see things concretely. Then the stabilizer of the zero vector is always the whole group. The stabilizer of any non-zero vector is conjugate to the stabilizer of E1. Now, E1 is the standard basis of Fn. Standard basis of Fn. Now, it is easy to see that the stabilizer of E1 is nothing but all the matrices, invertible matrices whose first column is E1. Okay. Similarly, for SL and F, the stabilizer is all the matrices with determinant 1 whose first column is this. Okay. So, we have just talked about actions of GLV and SLV. Now, let us come to the action of this group, which we have already also seen earlier. So, for any vector space V, if we consider the multiplicative group of the field that acts on V, okay. So, what are the orbits under this action? Of course, zero vector, no one is going to move the zero vector. So, that is a singleton orbit, trivial orbit, let us forget that. Now, for any non-zero vector V, the orbits are so alpha V, where alpha not equal to 0. So, therefore, this is basically the whole line one dimensional subspace generated by V punctured at the origin. So, to have to see the picture, we may take F to be Rn. Then basically the situation is as follows, that if we take if V is the vector, then it gives the entire punctured line. Okay. So, thus here the orbits are all the punctured lines punctured at the origin and the trivial origin itself. Okay, now let us talk about the action of orthogonal groups. I think with that I will finish soon. So, let us take the orthogonal group of Rn. So, this is the group of all n by n orthogonal matrices, certainly that acts on Rn. So, taking things over Rn, actually there is an advantage that we can draw pictures and have a geometric visualization for that. So, in this action, what are the orbits? Forget about the trivial one, then what about any other orbit? So, if V is a non-zero vector and A is any orthogonal matrix, then norm of AB is same as norm of V. So, first we see that all the translates of V are going to have the same norm. That means that this action certainly cannot be transitive. Now, the point is what is the orbit? So, that is quite, I would say, easy to see that first of all let's first calculate compute the orbit of E1. The orbit of E1 is simply, you can see the unit sphere x1 square up to xn square, okay, x1 up to xn, such that okay, this is, you can immediately see that is because of if U is any unit vector, then you can indeed extend that to some orthonormal basis of Rn. Now, you map the standard orthonormal basis to that orthonormal basis whose first vector is U, and the corresponding matrix gives you, the corresponding matrix works. So, we see that so this is the n minus 1 dimensional sphere Sn minus 1. So, the action of ONR on Sn minus 1 is transitive, and from this we can see the following, that if two vectors are having the same length, suppose V and W are having the same length, let the length be something, let us say L, then we say V mod L and W mod L, both W by L both lie in this unit sphere, both are lying in this unit sphere. Okay. Hence, there is an orthogonal map sending this to this, which implies AV equal to W. So, thus in view of all this, we see the orbits are the sphere centered at origin with all positive radius, and if you want to include the 0 vector origin itself, then we should allow 0 radius as well. So, a sphere centered origin with 0 radius means the 0 radius so is defined to is nothing but the point itself, the point origin itself, the singleton origin. So, thus under this action orbits are the spheres. Similarly, if you follow the way we worked out everything here, so well, this may not work, but however I would like to leave this to you. So, what happens SONR on Rn. Here actually in fact this is quite easy, I would say, because that will be fine. So, given any 2 points V and W, suppose they are in the same sphere. So, there is a orthogonal matrix sending W to okay, maybe I should rather work out this in this way, that if U is an unit vector, I have orthogonal matrix from this, that A which sends A U1 to U, right. So, if orthogonal matrix is determinant plus minus or plus 1 or minus 1, if it happens to, if this is determinant 1, then we are done, and if determinant minus 1, then we can multiply any column other than the first column by minus 1, that will not change the orthogonality. So, thus we can always choose this determinant to have, choose this matrix to be of determinant 1. So, it shows that SONR acts on this unit sphere transitively, and hence in the previous way here also we see all the orbits are just the spheres. Now, we will finish this lecture then by asking what happens in the complex case. So, in the next lecture we will talk about some more examples of orbits and stabilizers by actions by linear groups. Okay, so let me finish this lecture by this. So, consider the action of UN. UN is the group of all unitary matrices. So, okay, I might have written this earlier. Action of UN on Cn, what are the orbits, and similarly SUN on Cn. SUN is the unitary matrix determinant 1. Okay, so with that I will finish this lecture.